today we are going to look at more applications of depth first search in directed graphs. Recall that in the last class I had mentioned that we will talk about strong connectivity, right. We will see how to figure out if a given directed graph is strongly connected or not, and I had defined what strong connectivity means. Essentially means that between every pair of vertices, ordered pair of vertices, there is a path in the graph. So, which means I take two vertices, let us say u and v, there should be a path from u to v and also a path from v to u, then we would call the graph strongly connected, right. So, in the last class there was a very simple algorithm that was suggested, which was that take a vertex, do a DFS from there, take another vertex, do a DFS from there, and so on and on, which means do a DFS from every vertex in the graph. If in each one of these DFSs we include all the vertices of the graph, only then is the graph strongly connected, right. That should be easy to see. Let us see if we can reduce the number of DFS calls that we make. Instead of making n DFSs, can we reduce the number of DFS from n to, let us say, some smaller number. So, let us say I take one vertex v and I do a DFS from here, and when I do a DFS from here, I visit all the vertices in the graph. This is the, let us say, the DFS tree I obtain, and as you, and these, if these were the only vertices in the graph, then I have visited all the vertices of the graph. Yeah. So, what do I know? I know that there is a path from v to every vertex in the graph. So, if in my DFS from v, so if DFS v visits all vertices, then all vertices in the graph G, then there exists a path from V to every vertex in G, right. Suppose we could somehow figure out, so suppose we could also do the following. We could somehow figure out that there exists, or I claim that there exists a path from every vertex in G to V, right. Let us assume this is the case. Suppose this is true. Suppose this is true, that is हर एक वर्टेक्स से V तक पाथ भी है, then does that imply that the graph is strongly connected? So, basically we are saying 1 plus 2 implies G is strongly connected. Varum, why?
Because like once you reach V, then you can again reach any of the vertex.
Huh? Right. So, if you have to find a path between some two vertices, let us say x and y. So, what will I do?
X to V, then V to Y.
Go from x to v.
Then V to Y.
So, go from x to v. Yeah. By the statement 2, there is such a path. From every vertex to v, there is a path. And then I go from v to y. By statement 1, there is a path from v to y. So, all I need to somehow ensure is that there exists a path from every vertex in the graph to v. How will I ensure this? This says that there is a path from v to every vertex in the graph. If I can ensure that there is a path from every vertex in the graph to v, then I am done. How will I ensure that from every vertex in the graph there is a path to v?
From the lowermost vertex we are ending with the first starting backtracking from a path. If there exists a deepest package, deepest package from there.
Every leaf has a package.
Okay. So, this is the question. How do I ensure that there is a path from every vertex to v? So, how do I check? How do I check if there is a path from every vertex to V. How do I do this?
So we can consider back edges and so also
Think fresh, think of something new.
Also we need the cross edges to. So if there are some cross edges, so we can go along them to.
Suppose I were to do the following. I took my graph G and I reversed. किसी ने reversed बोला था. Reverse edges to get a graph G sup R. Reverse edges का क्या मतलब होता है? डायरेक्शन रिवर्स कर दीजिए. ठीक है. अब हिंट. अब इसको now do DFS. Okay, so do DFS V on this graph G sub super. तो अब क्या होगा? If all vertices are visited, तो क्या हुआ इसका मतलब? If all vertices are visited, मतलब हमने V सारे vertices visit हो गए. ये हमारा ग्राफ G सुप R है. सारे vertices visit हो गए. तो इसका मतलब क्या हुआ? हर एक वर्टेक्स के लिए पाथ है इसमें. तो इसका मतलब ओरिजिनल ग्राफ में हर एक वर्टेक्स से यहां तक पाथ है. If all vertices are visited, then this implies in G there is a path from every vertex to V. Yes or no? तो अगर सारे वर्टिसेस विजिट हो जाते हैं तो हम ये कह सकते हैं कि ग्राफ स्ट्रांगली कनेक्टेड है. If every vertex gets visited in this DFS, then I can say that the graph is strongly connected. अगर कोई वर्टेक्स नहीं विजिट होता है तो क्या मैं कह सकता हूं कि ग्राफ स्ट्रांगली कनेक्टेड नहीं है? अगर कोई वर्टेक्स छूट जाता है इस सेकंड DFS में, ये वर्टेक्स तक हम पहुंच ही नहीं पाए, क्योंकि हम यहां नहीं पहुंच पाए, इसका मतलब इन दिस ग्राफ देयर इज नो पाथ फ्रॉम V to this vertex, which means that in the original graph there is no path from this vertex to this vertex, which means that the original graph is not strongly connected. ठीक है, हो गया काम. तो कितना टाइम हमें स्पेंड करना पड़ा? कितने? 2 DFS करने पड़े बस हमें. हाँ, रिवर्सिंग एजेस करना पड़ा. रिवर्सिंग एजेस में कितना टाइम लगेगा? हर एक एज को जाके रिवर्स करते जाइए. We can also change the function DFS. Instead of looking at out adjacency edges, we can look at in adjacency edges, and we don't even have to reverse the graph then. Right? क्योंकि हम यही तो चाह रहे हैं कि पहले तो हम बाहर वाली एजेस लेके कहीं कहीं जाते थे. रिवर्स करने का क्या मतलब है? ग्राफ को रिवर्स करके जो अंदर आ रही थी एजेस उनको लेके अब हम DFS करना चाहते हैं. ठीक है. So essentially by using 2 DFSs, you can figure out if the graph is strongly connected or not. Yes? So everyone understands the procedure. Let me write down what the procedure is. Pick an arbitrary vertex V. Do DFS V. Reverse G. Do DFS V on G reverse. If all vertices are visited in both DFSs, then G is strongly connected, else G is not strongly connected. Is this clear to all? तो इसमें तो मज़ा नहीं आया, राइट, कि हमने सारा क्रॉस एज बैक एज सारा सीखा, कुछ का फ़ायदा ही नहीं हुआ, तो वो भी करते हैं आप. We'll now try to do it with only one DFS, right? It's an academic exercise for this problem, but at least you will learn, the properties of DFS, right? Because this is a perfectly fine algorithm, and it just requires 2 DFSs to do it. Okay, so let's look at another way of checking if a graph is strongly connected or not. And now we'll use our whole gamut of definitions and terminology, right? Okay, so what are we going to do now? We are going to do a DFS, right? We start from a vertex and we do a DFS. So let's say these are the red edges which form the DFS tree. वहाँ पे रेड नहीं दिख रहा आपको? Okay, suppose this is what I get my DFS tree as. Now, I remarked in the last class that we are going to use ideas similar to what we developed for 2-edge connectivity. So 2-edge connectivity में हम क्या करते थे? We were saying that when we are backtracking, let's say I'm backtracking from this vertex, I'm going back to the parent, right? Because I've finished everything, I ensure that there is some edge which goes from this subtree to where will it go? It can only go to an ancestor or above, right? Because we said there are only back edges in the case of undirected DFS. So if an edge goes out of here, it cannot go to one of these nodes. It can only go to an ancestor, right? So we said we would like to have one such edge. Now we need similar such thing in the case of strong connectivity. From here we would like that there is some edge going out. Out से क्या मतलब है? Out, यहाँ पे तो out, what kind of edges will be going out of this subtree? Only back edges, right? But if this was the subtree I was considering, right, then there could also be, either there is a back edge out of this subtree or there is a cross edge out of this subtree. So I could also have an edge going like this. Can happen, right? So this edge is also an edge going out of this subtree, and if there is an edge going out of the subtree, I am happy, right? Okay, so this is the only thing we will require. Clearly this is required, this is necessary. If from this subtree there is no edge going out, then this graph is not strongly connected. Why? Because then you can only enter the subtree, you can only come to these set of vertices, you cannot go out of these set of vertices. What I mean by that is that if there were no edge going out of this subtree, then I cannot go from this vertex to the root, for instance, to vertex V, because there is no edge going out of these 4 edges. This is like an island in itself, you can only come into here, but you cannot go out of here. Yeah, so all I am saying is that we require, it is necessary that an edge go out. Whether that is sufficient, we have to figure out. It is clearly necessary that an edge goes out of every subtree. You understand the difference between necessary and sufficiency, right? So it is necessary that an edge go out of every subtree. You understand what I mean by out of every subtree? So you're looking at a subtree. What is a subtree here? It is the descendants of any one vertex. Take any one vertex, look at all its descendants. That's the subtree we are interested in. Yeah, and there has to be one, at least one edge going out of that. दिस इज क्लियरली नेसेसरी. अगर हमें कोई ऐसा सब ट्री मिलता है जिसके नो एज इज गोइंग आउट ऑफ दैट सब ट्री, देन वी कैन स्टॉप द प्रोसेस एट दैट पॉइंट, स्टॉप अवर DFS एंड से दैट दिस ग्राफ इज नॉट स्ट्रांगली कनेक्टेड. Yes? Everyone with me? Now, we'll see how we can check this thing. We'll look at the procedure, we'll look at what modification to make to the DFS so that we can check that there is an edge going out of every subtree. The check would be very similar to what we did for the case of 2-edge connectivity. Right? But now let's see that this condition is also sufficient. If from every subtree there is an edge going out, then the graph is 2-edge connected, the graph is strongly connected. Huh? सबको दिख गया? Yes? Why?
Arrival times are decreasing.
Of what?
All the subtrees, if there's an edge from here to some other subtree,
Yeah,
the vertex that it reaches will have a lower arrival time
will have a lower arrival time than whom?
than the vertex over here.
Then all the vertices are separate.
Okay, good. Close. Almost there. So what am I going to do? देखिए, from the root I can reach every vertex. Now all I have to show you is that from every vertex I can reach the root. If I can reach the root from every vertex, I am done. Yes? Because then how do I find a path between x and y? I go from x to the root, and from the root I go to y. So all I have to show you is a path from every vertex to the root. So we want to find a path from every vertex to the root. अब हमारा ये पाथ किस तरह का बनेगा? We take some vertex. Right, let's say this is a vertex x. I want to go from x to the root v. How will I go? Well, I am going to look at the subtree rooted at x. देखिए, x is some vertex somewhere in my DFS. उसके जो descendants हैं, मान लीजिए वो ये descendants हैं. ठीक है, इस subtree से एक edge बाहर जा रही है. वो edge या तो back edge है, right, या cross edge है. अगर बहुत एजेस बैक बाहर जा रही हैं, उनमें से कोई भी एक को पकड़ लीजिए, कोई फर्क नहीं पड़ता, कोई भी एक ले लीजिए. ठीक है, अब इस एज, इस नोड का अराइवल टाइम, ये वाला जो नोड है इसका अराइवल टाइम, विल इट बी स्मॉलर देन एक्स और लार्जर देन एक्स? स्मॉलर देन एक्स. एंड ये वाले नोड का अराइवल टाइम smaller, because this is a cross edge. We would have first come here. In fact, इसका departure time भी इससे smaller होगा, right? Yeah. So let's give this name. Suppose this node is W, right? So I can reach a node W. So now what have we said? We have said that from X, can I go from X to W? Yes. Yeah. Why? Because this is a subtree. These are all descendant. This node is also a descendant of x, which means that I can come to this node and then I can take this edge and get to W. So what's the big deal about getting to W? From x I can get to a node which has a strictly smaller arrival time than x. Yeah. Now from W I can repeat the same process. From W I can get to a node which has a strictly smaller arrival time than W, which means that maybe यहाँ में W आया था, यहाँ से मैं एक और क्रॉस एज लेके A पर पहुंच गया. ठीक है, यहाँ से मैंने एक बैक एज लेकर कहाँ पहुंचा? C कर देता है, C पर पहुंच गया. ठीक है, ऐसे ऐसे मैं चलता जाऊंगा. But now what do you know? You know that the arrival time of x is strictly larger than the arrival time of W, which is strictly larger than the arrival time of A, which is strictly larger than the arrival time of C. So हर बार I can get to a node with a smaller arrival time. तो कब ये प्रोसेस मेरा खत्म होगा? when I reach the root, right? So that will give me a path from this node to the root. Okay? So just this requirement that an edge go out of every subtree is both necessary and sufficient. Just this requirement, and this is an easy requirement to check. Yeah, and we are going to do that next. So everyone with me? So how am I going to check this requirement? So how should we modify DFS so that we can check if there is an edge going out of every subtree, right? I am using the word subtree a bit loosely here, right? Here I am, by subtree I mean the part of the tree which is composed of the descendants of any vertex, right? So take any vertex, look at all its descendants, that part of the tree is what I am calling a subtree, right? The generic definition of a subtree is slightly different, right? So how will we modify DFS to be able to do this? So once again we are going to, so recall that in the case of 2H connectivity we had modified DFS so that it returns to us the deepest back edge, right? The arrival time of the node to which there is a back edge from this subtree and the smallest such arrival time. याद है सबको? नहीं, right? In the case of 2H connectivity, what we had done was that we would return from every subtree would return the deepest back edge. By that we mean the arrival time of this node. Yeah. Now we will do the same thing here. This DFS would return to us not the deepest back edge anymore. The node with the smallest arrival time to which there is an edge from this subtree, right? So let me write that down. The DFS returns arrival time or returns what should I say, the smallest arrival time the smallest arrival time to which there is an edge from this subtree, from the subtree rooted at, let's say, V. So DFS V returns this, right? So what I am trying to say now is the following: when I do a DFS from V, there could be many edges going out of this subtree. Right? Let's say there are 4 edges going out of this subtree. An edge which is going out of the subtree will either be a back edge or a cross edge. Forward edge cannot be going out of the subtree, right? It can only be coming into the subtree, or if it starts from here in the subtree, it will go within the subtree only, right? So now essentially I am going to look at these 4 arrival times, and take the smaller amongst them, the smallest amongst them, and that is the quantity that DFS V will return to me. Right. So, if this arrival time was A, this was B, this was C, and this was D, so DFS V returns min of A, B, C, D. Right. Clearly, B is smaller than A, right, and D is also smaller than C. Oh, not clear. Okay, but we will come to this. This is what we have to return. Now we have to figure out how we will return this thing. Yeah. So how will we return this thing? How should? So it's note that DFS is a recursive procedure, right? So when I do a DFS from vertex V, I end up doing a DFS from its neighboring vertices, right? So suppose its 3 neighboring vertices were X, Y, and Z. So I will do a DFS from here, I will get this tree, let us say. I do a DFS from here, I get this tree. I do a DFS from there, I get that tree. Now this DFS X will return to me. DFS X will return something to me. So it will look at all the edges which are going out of this subtree and look at the node with the smallest arrival time to which there is an edge from here. Similarly, DFS Y would return something to me, and DFS Z would return something to me. So what is the value of DFS V going to be? DFS V would have a value. We have to find out the edge going out of this subtree. So an edge which goes out of this subtree would be an edge going out of here or out of here or out of here. But an edge going out of here could end up here itself, right? So it's not really going out of this subtree. Huh? And we'll also look at V, of course. So from V we will look at the back edges out of V and the cross edges out of V. So we'll basically look at all the edges going out of here, all the edges going out of here, all the edges going out of here, and all the edges going out of V, and take the minimum of their arrival times. Okay, and when will that? Okay, and when will the edge be going out of this subtree? When that arrival time is less than the arrival time of V. Yeah? क्योंकि ऐसा भी हो सकता है आपसे कि यहां से तो जो स्मॉलेस्ट है वो यहीं तक जा रही हो, यहां से जो स्मॉलेस्ट है वो यहीं कहीं जा रही हो, यहां से जो स्मॉलेस्ट है वो यहीं कहीं जा रही हो. ठीक है, तो इन सब से तो ऐसा था कि देयर इज एन एज गोइंग आउट, बट इस पूरे से देयर इज नो एज गोइंग आउट. हो सकता है ऐसा. सो यू हैव टू चेक दैट जो आपके पास ये नंबर आया इतना सारा मिनिमम लेने के बाद, that is less than the arrival time of V. If it is less than the arrival time of V, then that means that the edge is going out of the subtree and we are okay. If it is not less than arrival time of V, then we can stop the procedure and say that the graph is not strongly connected. So now I just have to write the code for this. So what should I do? Let's call this strongly connected. Right. So what is strongly connected going to do? So first, it's going to be setting up the arrival time of vertex V. Yes. Now what should I do next? Right. I need to keep track of this minimum. So I need a variable for that. Right. So let me declare some variable. What should we call it? Min. No, min is for the function. So what should I call it? You can't think of a name of a variable? Huh? X, y, z, huh? That's how you name your variables. Okay, let's call it x, y, z. So what should my initial value of x, y, z be? Arrival of V? No harm in setting it to this value. Yeah? And now what am I doing? What should I write next? For all W adjacent to V. Out adjacent is the same as adjacent. We are saying adjacent means out adjacent here. Adjacent to V, do what? If not visited, huh? Oh yeah, somewhere I have to set visited V equals 1. Right? As soon as I start a DFS, I set the visited variable to 1. If not visited V, then what do I do? Then I do a DFS from there, or I run this procedure from that vertex W, and it will return something to me, and I have to update what it returns. So XYZ equals minimum of XYZ comma SC W. Yes? Else if visited W is true, if the vertex W is already visited, so then that means that it's either a cross edge or a back edge starting from V. Else XYZ equals min of XYZ comma arrival of W. Yeah? What are we doing here? We are looking at the cross edges and the back edges starting from the vertex V, right, and also including that into the min computation. And now what remains? This is the end of this for loop. Huh? If XYZ equals arrival V, then stop, right, and we'll stop with saying that graph is not strongly connected, else we just return. Yes. This will again have a small problem for the root vertex, because for the root vertex this quantity will only turn out to be 0, cannot be less than a 0. Yeah. So that has to be checked. We can't abort always, we have to just ensure that it's not the root vertex. Okay? It's almost exactly like we did for 2H connectivity. Questions? नहीं, कोई questions नहीं? Good. So how much time does this take? Almost the same time as depth first search. Right? We are just again the same. We have one additional variable which you are modifying, and that's all the time, the additional time we require. Great. So, so as far as applications of DFS are concerned, you have seen quite a few applications. Can someone tell me what all you have seen? Application of DFS to directed graphs. Or application of DFS in directed graphs. Sorry. What are the applications we've seen so far? Huh? 2H connected is not for directed graphs. Strongly connected. Checking if a graph is strongly connected. Checking if a graph is acyclic. Yeah, and of course also topological sort, although it's the same as that. Yeah, there are a whole lot of other applications. I am not going to be taking them up in this class. Right? Any questions so far? Right. So, as a recap, let's, since we are now going to be switching topics, let me also look at what we have done for the undirected graphs. Right. So, we actually have only looked at one application, that was for 2H connectivity. I did mention that you can use similar procedures, you can use DFS to also check if a graph is vertex connected and if it is planar, right. But we did not do those two applications in detail in this class, right. And what application did we see for breadth first search? Applications of breadth first search. Connected components, finding the connected components of a graph. And checking if a graph is bipartite. Right. Huh? Shortest distance also. That's just breadth first search. The labels that it returns are the distance, the shortest distance of the vertices from the root, the starting vertex. Right. And all of these are linear time procedures. All of these. Okay? Yeah.